Okay, and we are ready to go. Okay, guys, today we will be talking about files and low-level input-output in the world of POSIX and especially in the world of Unix. We will take a look at the four fundamental system calls: open, close, read, write for file manipulation, and to some additional system calls. Plus, we will talk about redirection, how the file systems are implemented in a Unix operating system, the statistics that are available for files, how to create temporary files, the relationship between descriptors and open files, and finally, we will talk about how buffering works in a standard POSIX system and what to pay attention to. So, files, files, files. Why are files so important? Files are important because in a POSIX compatible system, and especially in the world of Unix, everything or almost everything is represented by files. Files are represented by files, devices are represented by files, processes have even corresponding files in order to reach them. But everything, basically, as an API, as an interface, is available as a file. So if you want to access some piece of hardware, you go to a file that represents that piece of hardware. If you want to access a directory, you also go to a file. Links, sockets, inter-process communication mechanisms, they are all represented as files. And as such, of course, we need to be sure that we know how to handle those files. We know how to open them, close them, read from them, write to them, and what are the possible pitfalls, what are the possible traps, problems that we might encounter in those cases. Now, if you use your familiar command ls, the type of the file is of course available, as some of you might know and some of you might not know, is available as the first character of the ls command output. Now for regular files, you can see only a dash as the first character. For directories, you will see the character D. For character devices, you will see the letter C. And for block devices, you will see the letter B at the beginning of the corresponding file's ls output. Now C corresponds to character devices. And what is the difference between character devices and block devices? So between C and B. C corresponds to character devices which stream sequential data. Bir bilgi, bir veri akısı. A sequence, a flux of data, 1 byte at a time. Whereas in the case of block devices, such as hard drives, they provide random access to blocks of data. So in one case, you read bytes 1 at a time as a flux of data, but in block devices, you read entire blocks and you can read them in a random access strategy, which is not possible with character devices. Other types of files, well, of course, the pipes represented by P. We will talk about pipes during the week of inter-process communication. Symbolic links, sockets, also a piece of IPC represented by respectively by L and S. Now, all of these are files. All of them are files with different purposes. Now, we don't care about their purposes. What we care about is how to manipulate those files. Now, what is the organization of those files? Well, nothing fancy. Well, depends on who you ask. They are all organized within, of course, a file system, which is represented as usual as a tree of files. At the root, of course, we have the slash character representing the root of the entire file system. And underneath it, of course, we have the usual directories containing subdirectories and files. Now, what are the most important directories that you will encounter in all of the file systems? There will be, of course, the bin directory containing the system binaries, etc for the configuration files, sbin for the really essential system binaries, such as the reboot command, such as the fdisk command, the USR for the read-only user application, support data and binary, so basically the programs that you have installed to the system, var for the variable data files, so logs, libraries, cache files, and so on, and of course dev for the device files, home for the user home directories, lib for the libraries, mnt for the mount points of external devices and file systems, proc for the process-related files. We will get to that in one of the upcoming weeks. And of course, the root directory containing the root user's home directory. Now, a difference between the Windows systems and the POSIX systems is that in the case of Windows systems, as all of you probably know, it is the device letter So C device, D device, and so on, that represents the root of the file system. We don't have that in POSIX. That is against the rules of POSIX. In POSIX, the root of the file system is represented by the slash character. And it can contain underneath it multiple drives. It is possible. You can mount multiple drives, multiple actual devices, CD, whatever drives you have, into or onto the same file system. That is not possible in Windows. In Windows, each drive has its own separate file system. So that's a fundamental difference between the Windows and POSIX compatible systems. Now, of course, you know what is a relative path and what is an absolute path. I'm not going to talk about that. What I am going to talk about is that in most of your homeworks, in fact, in all of your homeworks, I expect your homeworks to work with both relative and absolute paths. So please keep that in mind. So do not only test your program with absolute paths, because I or the assistants might test it with relative paths as well. An important point: every directory in a POSIX system contains the files dot and double dot, which of course represent the current and parent directories. You do not create them. They are available by the kernel, and they are at our disposal in order to make our life easier. So we can manipulate them in order to access the parent directory and so on. Here, for instance, we have an example where we use the double dot in order to access the parent directory, in order to get access to some file, whatever, inside it. Now, what about the programming part? Let's get to that step by step. In a POSIX compatible system, we open the files, of course, by using their file names, but once they are opened, we only manipulate them by using the file descriptor returned by the open system call. So at a system level, files are represented, open files are represented by integer file descriptors, non-negative integer file descriptors. So for example, 0 is standard input and so on. Now, especially in the case of the first three, 0, 1, and 2, as file descriptors, as non-negative integer file descriptors, they are already open the moment that your process starts to execute. Who opened them? The kernel opened them. What do they represent? 0, 1, and 2. 0 represents the standard input device, of course, as a file, as an open file, which is usually the keyboard. 1 represents the standard output file, which is usually a monitor. And 2 represents the standard error file, opened, and it usually points to the same place as the standard output by default. And of course, it is at our discretion, at our disposal. We can change them in any way we like. So we can close the keyboard as input device, and we can open up 0 as the scanner. So whatever we read from the scanner will become the output of scanf or fscanf or whatever. Now the key for system calls for input-output are open, read, write, and close. They are easy to manipulate. We will take a look into the specific system call parameters in the upcoming slides. But for now, just superficially, what does open do? It opens the file whose path name has been given to it and returns the file descriptor, returns the corresponding file descriptor as an integer. What does read do? It reads from the already open file descriptor represented by FD, count number of bytes into the buffer that has been given as a parameter. Write, it writes to the file descriptor, to the open file descriptor FD, count number of bytes that are located in the buffer. And of course, closes the open file descriptor represented by FD and returns all the allocated resources back to the system. Now, let's take a closer look. The open system call. Now, at the top, you can see the function, the system call signatures, and the necessary header files. Whenever you need additional details about a system call, what do? Which command do you use?
Man command. Man.
Yes, we use the man command. So in the particular case of open, I can readily access all of this information. So what does it do? What are the possible values for the parameters? What does it return? What are the possible errors? Example of use, and so on and so on. Everything is available at the man page. So whenever you have any doubts about how to use any system call, or even if you don't have doubts, make sure that you occasionally read the man pages in order to keep your knowledge fresh. Now, the open system call comes in two flavors, with 2 parameters and 3 parameters. The parameters are, of course, the path name of the file to open, the flags, and the mode. Now, the path name is obvious. It can be both a relative path name or an absolute path name. But what about the flags and the mode? Now, the flags denote in which framework, in which context we are going to open this file. And it can only take constant values. Now, these constants are already defined in the header files that you include. There are many possible values that you can use. The entire list is available in the man page. The most important ones, in my opinion, are, of course, read-only, which means the file will be opened, well, obviously, in read-only mode, so you will not be able to manipulate it, modify it, or write-only, only for writing, read or write, so both flags simultaneously. This is an important one, or create. If you use this flag, that means the file will be created. If it doesn't exist, it will be created. If you don't use this flag and you try to open a file that doesn't exist, well, in that case, it will return an error. Append means that you will open the file and whatever you try to write to it will be appended to its end. If you use this flag or trunk, it means that it will open the file and it will empty it. O exclusive is also quite useful. It is in 99% of cases used together with O create. How do you use them together? By ORing them, logically ORing them. So you can use multiple flags with the OR operator, the logical OR operator between them. We will look at examples. So for example, if you use O create and O exclude or O exclusive together, that means it will try to create the file with the path name that you have given to it. And if the file already exists, it will return an error. If you use only O create, it will create the file, and if it already exists, it will not return an error. It will just open it. There is also non-block, which means that if it cannot open the file for any reason, instead of blocking, it will immediately return an error. And of course, there are many more. If by any chance the open system call fails, it will return -1, and of course, it will set the errno global variable. Now, okay for the flags, but what about the mode? What is this mode? Now, the mode also is a combination of constants that you can combine using the binary logical OR operator. And what it represents is basically the permissions with which a new file will be created. So let's say that you want to create a file. Now, is this file supposed to be accessible by the user? Is it supposed to be executable? Is it supposed to be writable? Is it supposed to be writable by the user, by the owner of the file, by the group of users, or by everybody else? So somebody needs to determine those permissions. Now, you can, of course, provide those permissions at the moment that you try to open the file, so indirectly creating it. And of course, we have the entire range that's available to us. We have 9 different constants, each 3 of them available for the respectively the user group, the group, and the others group. And those 3, of course, represent the read permission, the write permission, and of course the execution permission. Now, what do those permissions mean exactly? Now, in the case of a normal file, well, obviously you can read it, write it, and execute it if it is binary. Writing to it obviously means modifying it. But what if that file is a directory? Now, if it is a directory, being able to read a directory implies the ability to list all the files in the directory. So having the permission to read the directory means being able to see what it contains. So which files are in that directory. Being able to write into a directory means that you can actually create new files in a directory. And being able to execute, well, for a file, well, basically it means that you can execute the file if it has an execute permission, if it is a binary file. But for a directory, it means that you can enter the directory. So if you do not have the execute permission, you cannot enter the directory. You can read it, so you can see what files are inside it if you have the read permission, but without execute, you cannot get inside it. Any questions about this part?
Hocam, should we have to execute after we did the manipulation on that file, or it is already executed without we being executing them?
I didn't understand that question. So you are manipulating a file, so you have opened it. So why do you need execution after opening it?
If we have to manipulate it, we have to do some stuff, right?
If you want to manipulate it, first you have to open it.
Correct.
Using the open system call. So you have opened the file. Okay.
Okay. We want to do we want to do some manipulations on them?
By manipulation, you mean reading and writing.
Correct. Do we have to also use the execution call after while we are doing this manipulations?
What do you mean execution call? Do you mean the execution permission?
Yes.
Now, these permissions, they come into play only when you are creating a new file. Only when you are creating a brand new file that didn't exist before. So if your intention is to read and write to that file, well, in that case, you don't need an execution permission. If your intention is to read to it, so you must have at least the read permission. You must have at least the read permission for the user. If you intend to also read and write to it, you must have the read permission and the write permission for the user. So basically for the owner of the file. If you also intend to execute the file afterwards, after closing it for whatever reason, well, in that case, yes, you must also give it an execute permission. But if your intention is only to read and write to that file, not a directory, but to that file, well, in that case, you only need the read and write permissions. The execution permission for a file, you only need it in case you intend to afterwards actually execute a binary file, so a binary file that you want executed, or a script or whatever, or if it is a directory, you want that directory to be allowed for entering from the outside. So you want other users, other processes to be able also to enter that directory. What I'm trying to underline here is that the permissions have different meanings depending on whether the file is an actual file, a regular file, or a directory. Whichever you choose depends completely on what you require for your particular application. You have complete freedom. You can pick whatever you want. But do not forget that what the final permissions of that newly created file are going to be also depend on the system UMask and the access permissions of the parent directory. So let's say that you want to create a file inside a directory, but that directory hasn't given you permission, hasn't given you a write permission. So you are inside a directory for which you have execution permission with your process, so that means you can enter it. But if you do not have a write permission for the directory where you are located, even if you try to create a file, giving the proper permissions, you will not be able to achieve that. Why? Because the parent directory is not allowing it. So whether those permissions that you have requested for the newly created file are going to be realized or not depends on three things. One, the permissions that you ask from the open system call. Two, the UMask, so the default kernel level, default new file permissions, which you can manipulate on a user level. And of course, the access permissions of the parent directory. All three of these come together in order to determine what the final permissions of that file are going to be. So you do not have the sole authority when deciding the permissions of a file that is going to be created. You make your request from the kernel, and the kernel takes into account both the UMask, so the user level default permissions, and of course the access permissions of the directory where you are trying to create that file. Questions?
It was perfectly clear, sir. Thank you.
Okay. Example. Here we have a simple example, not a very good example, but it is simple. This is from the Advanced Linux Programming book, which I highly recommend. So our main function, argc, argv, they're all there. We get the path of the file to open as a command line argument. So path contains the command line argument. So here we have the permissions of the new file. So what are the permissions that we want that are logically with an OR operator combined? We want read permission for the user. We want write permission for the user. We want read permission for the group, write permission for the group, and read permission for all the other users. Okay, so we combine these 5 modes into one as an octal value. We call the open system call with the path, and we can see that we have 3 flags: write only, O exclude, and O create. Now this means we want to create a new file, and if that file exists, we want an error to be returned. So we do not want to overwrite a file in any way or open an existing file. We want to create a new file, absolutely. So we are using O exclusive together with O create. And we also want to open it in write-only mode. Afterwards, we are checking, of course, if the file descriptor is -1 in order to be certain that an error hasn't taken place. If an error has taken place, we use our old friend perror in order to print it on the standard output. We return 1 and we exit the program. Otherwise, we don't do anything and we just return 0. Remember, 0 is reserved for normal execution. Negative values are reserved for errors, and positive, strictly positive values are reserved for extraordinary situations. Now here we also have the octal representations in numerical format to the right in order to see to which numbers they correspond. The read-write execution. So the first group of 3 letters, read-write execute on the left, correspond to the permissions of the user. The middle 3 characters correspond to the permissions of the group, and the 3 characters to the right correspond to the permissions of all the other users. What about closing an open file? It's very easy. You just call close and you give it the file descriptor corresponding to the open file that you want to close. It returns 0 on success and -1 on error. Hocam, how many open file descriptors can I have? Well, the typical limit is 1024 per process. So every process can have at most 1024 open files. Now, this is not an absolute limit. You can modify it by using the getRlimit and setRlimit system calls, but I do not recommend it. If you have a program that requires more than 1024 open files at a given moment, maybe you should check your program's design. That is not a good sign. Okay, the big boys, writing and reading. Now, the write system call has 3 parameters, as you can see. It is supposed to write to the file descriptor fd. At most, en fazla, at most count bytes that are contained in the buffer boof. Now, as you will see from the function signature, the type of boof is a const void pointer, which means that it doesn't have to be a character array. It can be an array of anything. So there is no limitation. Ufak bitiyor arkadaşlar. Yüksek lisans başvurularında hocalarımızın bir tanesinin çok sevdiği sorulardan biri void pointer nedir? Parantezi kapatıyorum. Kim olduğunu söylemiyorum. Now, the write system call will write at most count bytes to that file. It won't necessarily write exactly count. And what does it return? It returns the number of bytes that it has written successfully or -1 on error. So what can go wrong during writing? A lot of things can go wrong during writing. These are the possible errors. So for example, ebadf, the file descriptor is not valid. Einter, very common. The call was interrupted by a signal before the data was written. EIO, a low-level input-output error has occurred. No space, there is no space left on the device. We are trying to write bytes, but the disk is full, and so on and so on. Example. appending a timestamp to a file. We have a simple function, get timestamp, which simply uses the library function time to get the number of seconds since the epoch. It converts it to a human readable format by using local time and ASCII time. And what is happening in the main function? Well, we have the command line arguments available to us. The file to open is provided as a command line argument, as a path. We use the get timestamp function to get the timestamp as a character array. We open the file using the file name. We open it using three flags in write-only mode. We want to create it, but if it exists, it will just open it. It will not return an error. And we are opening it for appending. So that means we will open the file, and the cursor, imlech, the cursor will be at the end of the file. So whatever we write into it will go to the end of the file. We calculate the length of the message to write using strlen, and we simply use write in order to write it. Of course, this is a bad example. Why is it a bad example? Because we are not checking whether those system calls have failed or succeeded. Write can fail, close can fail, open can fail, anything can fail. This is a bad example. This is here only to show you how to use the write command. Okay, so here we can see the output. So we call timestamp with the TS file on the right. If we cat it, so if we look at the contents of the file, you will see that it contains the current timestamp. If you execute it again, you will see that it appends one more timestamp to the end. Nothing fancy. Any questions about write? We have more examples, don't worry. Now, the read system call. This is a heavyweight system call. Now, it is a symmetrical system call with respect to write. It also has three parameters. The file descriptor, of course, from which we are going to read. The buffer, where we are going to store the bytes that we have read. And, of course, the number of bytes that we want to read. Same principle as write. It will return the number of bytes that it has read successfully. It will return 0 if it has reached the end of the file, and -1 if it has encountered an error. Now be careful. Another difference between the Windows and POSIX worlds, I'm sure that you already know this. In the Windows world, the ASCII files use 2 characters in order to denote the end of a row and the start of a new one. So at the end of every line, you will have 2 characters, the carriage return and the new line character. So \n and \r. Whereas in the POSIX world and Unix world, we only use the \n character in order to denote the end of a line. So be careful when you transfer files back and forth between Windows and POSIX systems, because if you create it in Windows and you open it in a Linux or POSIX environment, you will see that every row contains additionally an unwanted character at the end of each line. So be careful with this. It's a common bug. Example for the read system call. What do we do here? We receive a command line argument representing the path name of the file to read from, and we dump its contents in hexadecimal format to the command line. So how does it work? Let's see. So we have the main function. We have an unsigned character buffer of 16 characters. We have the offset and a variable to hold the number of bytes that have been read. Okay, that's nice. So we open the file in read-only mode. Okay, we are not checking whether it was successful or not. This is a bad sign. And then we have a do-while loop. Now what it does is constantly reads until it reaches the end of the file. Okay, so we read files with using read fd into the buffer, size of buffer, so 16 characters. We are attempting to read 16 characters. And what do we do then? We print those bytes that we have read, but we only print from 0 to bytes read. So maybe we have read less than 16, who knows? We jump to a new line. We update the offset to the number of bytes read. Why do we need the offset? Just for printing it on the screen. And we keep on going until the number of bytes read is equal to the size of the buffer. Sorry, as long as it is equal to the number of bytes in the buffer. So this means that if we reach the end of the file, So we are reading it in multiples of 16 bytes. So we will read 16, 16, 16, and eventually we will read a number that is less than 16. So 0 or some number less than 16. If that happens, that means we have reached the end of the file, according to this logic. And then we close the file and we return 0. But of course, this is not a good idea. Why not a good idea? Because during reading that file, a signal might take place, something might go wrong, and we might read less than 16 bytes, even though we haven't reached the end of the file. So in that case, the program will exit the loop, even though it hasn't reached the end of the file. So this is not a good logic. This is not a robust program. It is here only to show you how read works. We have better examples. And this is one of those better examples. Now, this is an example of a properly written program that very simply copies the contents of the source file to the destination file. So the main function just receives two arguments, two command line arguments, the source path and the destination, the target path. Okay, so argc must be equal to 3. Okay. If argc is not equal to 3, we are printing on screen properly how to use this program. I want you to always do this in your homeworks projects. Always have a function printing on screen how to use your program. Always. Now, what does it do then? It opens the source file. Is there a question?
Yes, but some of my friends can't connect the lecture. Actually, there is no join button.
There is no join button.
Yes.
So is this something specific to today? Is this the first time that this is happening?
Yes.
Yes, it's first time.
Hocam, aynı problemi ben dün başka derste de yaşadım. Belki Teams'le ilgilidir.
Maybe they can restart the app. So I'm not sure about it, but I get this
Working.
error too. So I restart the app and it works. I can join the app.
No one can
Both
join right now.
Android and Windows cannot join.
I'm using Windows right now, and I'm in the.
Okay, class. Well, in that case, I will exit it and restart it. And hopefully I will restart Teams too. And hopefully the problem will be resolved. Let's see. But I don't think that this is originating from my system. I think this is Teams related. So I'm shutting it down and I'm restarting Teams.
Thank you, sir.